Hi class, how's it going? This is going to be our first lecture in Stewart's Calculus book, 8th edition, like it probably says on the bookstore. Looking forward to meeting you guys over Zoom, not in person, here in a little bit, but we're going to start with our very first lecture of Calculus 2, and it's 4.1 called Areas and Distances. Okay, so probably haven't seen calculus in a while, or maybe you have, but there are a few things to make note of because there's a big contrast between calculus 1 and 2. So calculus 1, so calc 1 let's say, that is in the realm of what's called, some people will call this differential calculus. Okay, so you probably heard the word differential in your Calc 1 class, and as you might already suspect, it pertains to something, aka the derivative. So this basically means, it has something to do with the derivative. Okay, so remember we took a lot of derivatives, cranked that out, that's all you did in Calc 1 basically, There are some other stuff, but there's a lot of derivatives. Now, calculus 2 is concerned with what's called integral calculus. So, integral calculus. Now, you may or may not have seen this word before, but we actually dealt with roughly what this thing was, the integral, and it was like probably at the very end of your class, and we kind of called it the antiderivative. So the antiderivative. Okay, so even though differential, integral, they have different names, you can kind of see that they're already related. One deals with the derivative, the other deals with the antiderivative, and it's not a mistake, let's say, that this thing is called the antiderivative, and we're going to explore that in great detail in the coming weeks. So maybe let me start to motivate why this is called the antiderivative and why we study it and what it is. Okay? So the derivative did some kind of operation, if you recall. You gave it a function and then it spit out another function. So for example, if we had the function x cubed, do you remember if you stuck this into the derivative, if you take now the derivative of x cubed, we got another function, 3x squared. Okay, so x cubed, you take its derivative, you get 3x squared, some other function. Okay, now do you remember what happens when you take the antiderivative of this guy? So for now I'm gonna use a to mean taking the antiderivative, kind of like this thing here, d over dx meant take the derivative. If we take the antiderivative of 3x squared, and this symbol will get replaced with something later, not yet, but this a will go away. I'm just using this to mean antiderivative for now. This actually ended up being x cubed plus some constant c that we didn't know. Okay, and then, ignoring the fact that there's possibly some constant c here, we can see that when we took the antiderivative of the derivative, we get back the original function. So see, we got back f. So it's kind of like if you put it into, a little like processing plant. You first stuck in x cubed into the derivative, you got another function, and then when you took its antiderivative, you got back the original function again. So see, they're undoing each other, hence antiderivative. And this process kind of goes in both ways. It's not a one-way street. So now, again, if we take the function x cubed, let's first take its antiderivative instead of the derivative. So we're going to take the antiderivative of x cubed, and if we recall, this is going to be 1/4 x to the fourth. If you forgot, don't worry, we're going to go over this much more in detail. And then of course we have the plus c here. Okay, and then now let's take the derivative of this function. So now if you take the derivative of, okay, remember, since we're taking the sum of two things, the derivative goes to each term, yada yada, power rule, all these rules. This will end up finally giving you x cubed. So again, you see that, yes, now if you take the antiderivative of x cubed, you get some function, take its derivative, and you get the original function back. So these two processes are inverse processes of each other. They essentially cancel each other out. And so Calc 2 mainly deals with the study of the antiderivative, or what's called the integral, as we'll see. Okay? Now you may be wondering, okay, you've been talking about this antiderivative thing for a while now, but on the board you have areas and distances. Like, what does this have to do anything with the antiderivative? So that's a good question. And to draw an analogy from Calc 1 is, if you remember the derivative, what did the derivative do? What did it tell you? So assume we had some function. You know, we want to think about this geometrically. By geometrically, I mean a picture, so in a graph. So we had a function f of x, and you know, this is what the graph looked like, for example. And then let's say I picked some point like a right here. Then what does f prime of a tell me? F prime of a, what is this? Remember, this was the slope of the tangent line. At x equals a. Or maybe to be a little less confusing, we'll just say a. Where a is just some number, you know? So a could be 1/2, it could be 2, you know, who knows? Whatever. And so what do I mean by the slope of the tangent line? If you recall, the tangent line was the line that just grazed your function right at that point. This was the tangent line. Okay, so this line right here, the slope of this line is what the derivative is telling you. You know, and a, you know, this is some point a. What if you take another point b? So you take this point b. Then the slope of this line right here, so f prime of b is the slope of this line. Okay, so you pick some point in your domain, and then you have a tangent line for that point. And then the value of the derivative at that point is just telling you the slope of the line. So this slope is going to be larger than this one because it's much more positive than the other. But essentially, that's what the derivative tells you. It tells you the slope of the tangent line. That's how we interpreted it geometrically. Okay, so now you may be wondering, is there like a geometric picture for the antiderivative? And the answer is yes. And it has to do with exactly areas. So this is the idea behind the antiderivative. So say we have some function. Let's just say we're looking at the parabola. F of x equals x squared. Okay? And then let's say maybe this is, okay, so this is a function f of x equals x squared. And say that, for example, let me draw this maybe a little more symmetrically. Okay, this is nice and symmetrical. And say this is like 1 and this is negative 1. Okay? And assume that you want the area underneath this curve. So what do I mean by that? I mean this thing right here. Say you want this area. You ask, what is this area? You know, what the heck is this area in the blue underneath the curve? So this is the area under the curve, which you're probably going to hear like many times, many times. Area under curve. Okay? And the antiderivative can give you this answer. The antiderivative will give you this answer, actually. And it turns out, very interestingly, that this is exactly what the usefulness for the antiderivative is the question. The answer to this question is you take the antiderivative. It's another function. So let's see. Remember, what was the antiderivative of this? So antiderivative of x squared was 1/3 x cubed, right? So this is the antiderivative, and actually the area under this curve, the answer to this is going to be this. Area under curve equals, and then let's call this capital F of x. Remember, this is kind of the same notation we used, as if we had small f of x as our original function, we usually called the antiderivative capital F of x. This actually ends up being, miraculously, is it just ends up being the difference of sticking these points -1 and 1, this particular value in there. So you stick 1 into your antiderivative and subtract it from sticking -1 into your antiderivative, which is very amazing because all we are caring about is the endpoints, and somehow we get the area under the curve. And this will end up actually being 2/3, precisely right on the dot, which is very cool. I mean, this is amazing that the antiderivative is linked to the area under the curve. And we'll see why this question is so important, and it's not just some random, thing that math people care about, which I understand can be very weird at times. So the derivative is linked to the slope of the tangent line, and the integral, or the antiderivative, is linked to the area under the curve. And so the fact that the area under the curve is just the difference of the endpoints here is another big observation. And so when we put the two observations that we've talked about together, we get what's called the fundamental theorem of calculus. We're going to work our way to this, but this is just like an overview. So what's to come? What's to come is what's called the fundamental theorem of calculus. Okay, I mean, based off that name, it's probably not that big of a deal, probably just like a small thing, but we might want to draw our attention to it. just kidding. The fundamental theorem of calculus. So we already kind of saw roughly what it's saying. So it has two parts. The first part, the ordering doesn't really matter, is that derivative and integral are inverses, or inverse processes, you could say. Okay, we already saw that. We saw a nice example of that. And the second one is that if we have a function f of x and want the area from x equals a to x equals b. So, for example, in our case, it was -1 and +1, and our function was x squared. Then the answer to this is just the antiderivative at b minus the antiderivative of a. That's going to be the area under the curve. So if we have a function and want the area from x equals a to x equals b, this is the area under the curve. So that's very, very astounding result. Very, very amazing. And this is what we're going to work towards. So we're not there yet, but this is the idea of what the first chunk of this course is going to be building up to, is this fundamental theorem of calculus, and we're basically going to see this happening pretty regularly. Okay, so now let's get to basically, the details. So we're going to start with some details now. And to do so, we basically want to talk about how to find the area under the curve without resorting to this fancy theorem that we had. So, let's take this as our example, and this is just straight from the book. So my hope is that if I follow the book examples, you guys will be able to follow along with that pretty easily and get a nice reminder. So this is going to be f of x equals x squared on the interval 0 to 1. Okay, so we're just looking at a small chunk of the parabola. And it's not the left half, just from 0 to 1. Okay? So here's 1, the output here is 1. And we can break this up. We can say that this is a fourth, this is a half, this is 3/4, all the way up to 1, and then, maybe it's worth it to put the output. So if you square 1/4, you get 1/16. So this point here is 1/16. If you square a half, you get 1/4. If you square 3/4, you get 9/16. And then if you square 1, you get 1. Okay? And you'll see why in a second that I'm drawing attention to these points. Okay, so we want to calculate the area under the curve here. And how many things do we know the area of exactly that are curved? Basically, not too much, maybe like an ellipse and a circle, but that's not going to help us out too much here. We do know very well the area of things that are made out of straight lines though, like rectangles, triangles, and things like that. So the idea here is we're going to approximate the area underneath the curve with rectangles. So this is the big idea. This is the idea that we have. Use rectangles. So we're going to use rectangles to approximate the area. Okay. And you probably cannot even read the fact that this says rectangles at this point. Let me rewrite this. Okay, and now if we're going to use rectangles, let's recall what the area of a rectangle is. The area of a rectangle is base times height. So you multiply the base of it times the height of it. Okay. Now what we could do is, I've very conveniently picked out these 4 points, and so we can use these 4 points to estimate the area under the curve. So what do I mean by that? So right here, we have some width right here of 1/4, right? So I can make a rectangle of width 1/4. So that's going to be my base. But how high should I go? Well, the function takes on the values anywhere from 0 up to 1/16 in this interval. I can, use any of these to determine the height. But what I'm going to do is I'm going to pick the endpoint, what's going to be known as the right endpoint. So for now, let's just pick the biggest number basically in the interval as the height. So I'm going to draw my rectangle at the height 1/16. So it has width 1/4 and has height 1/16, so it looks like this. Okay. And then I'm going to say, here's the area. Okay, so that's one small area that I'm going to use. As you can see, I've already counted way too much, right? This small piece right here, that's the area we're looking for. Everything above it is kind of an overestimate, but that's we're going to see how to overcome that in a second. So that's why it says approximate, because it's not going to give you the right answer exactly. Okay, next up, we're going to do the same thing. Now, the width of this interval is also 1/4. Because, if you take 1/2 minus 1/4, that's a fourth. So this width is also 1/4. And so I can make another rectangle with the same width of 1/4. And again, I can pick any of these heights right here. They correspond to numbers here. I can pick any height that I want, but I'm going to pick the one that corresponds to the right endpoint again, the height right at 1/2. So the output of the function at 1/2 is 1/4. So I again, now this width here, I'm going to go up this much, and then the width needs to stay the same. And so I get that. So again, a width of 1/4, but the height is going to be at 1/4 as well. So then I have this area, which again, we're overestimating, but that's okay. And then I'm going to do the same thing here. Another width of 1/4, and then I'm going to take the height at the output, the right endpoint here. So we have this. So the width is this much, and the height I'm taking to be 9/16, which is completely fine. Again, you could have picked any number in this interval from 1/4 to 9/16, but this is just kind of one method of doing it. So then we get this area, and then last but not least, we take this width again, and then the height of 1, and we get this rectangle. Okay. So this is a roughly the area. Sorry, this should be cut off like right here. Okay, let me fix that.
Hello, please leave a message after the tone.
Sorry about that. Okay, so that's 1, and that's all the way up at 1. Okay, so we have a rough idea of what these areas should be, okay? Because we know the area of a rectangle is base times height. So what we're going to do is we're just going to add up these areas now, okay? So maybe I'll say A1, this area I'm going to call A1. This area I'll call A2, this one is A3, and this one we'll call A4. Okay, so the area under the curve is approximately A1 plus A2 plus A3 plus A4, right? You just add up each of these areas. But as you can see, it's an overestimate, which is fine. That's completely fine. Let's see what it's going to be. So, for example, this is going to be, so A1 is going to be the width of this rectangle, which is 1/4, times the height of the rectangle, which is 1/16, plus, okay, again, this width of the rectangle is another 1/4, so another 1/4, times the height of the rectangle, which in this case is 1/4. Plus, and then A3. So again, this is always another 1/4. And then this time it's 9/16. And then last but not least, we have 1/4 times 1, which the height of this guy is 1. Okay, now to save you some time, notice that this factor of 1/4 appears every time in each term, and that makes sense, right? We always took the base to be the same length. So to help with your calculations, what you could do is you can pull out this 1/4 and essentially just add the heights. So we're going to factor out this 1/4. And then instead add the height, so 1/16 plus 1/4 plus 9/16 plus 1. Okay? And then when we do this, we essentially get 15/12. So when you do all this, you get 15/12 when everything reduces and things like that. Which this is approximately going to be 0.47, let's say. Okay. So with this way of estimating the area, we get 0.47, roughly. Okay? Now, remember I said that we were taking the right endpoints. So let me erase some of this, sorry, limited board space. And kind of summarize what we have. So using the right endpoint. So using right endpoint, area was approximately 0.47. Okay, and what do I mean by right endpoint? Remember, we pick basically the number on the right of each interval here. Okay, and I'll redo this so you can see what I mean. So instead of using the right endpoint, we're going to use the left endpoint, just as a comparison. Okay, so let's basically just redraw what we had. So this is 1, that's 1 again, and then let's say this is a 1/4, this is a 1/2, this is 3/4. So again, the output here was 1/16, the output here was 1/4, the output there was 9/16, and then we have 1. Okay, so instead of using the right endpoint, we're going to use the left endpoint instead. Okay, so what do I mean by that? So last time we broke down each of this whole interval 0 to 1, we broke it down into 4 sub-intervals. The interval 0 to 1/4, 1/4 to a 1/2, 1/2 to 3/4, and 3/4 to 1. Notice the width of each of these is a fourth. So each of these had a width of a fourth, and we kind of just looked at the function on each of these small subintervals. And the right endpoint was exactly these numbers. We took the biggest number on the interval. You know, it's called right endpoint because if you look at these things on the number line, here's 0, here's 1/4, this is the right point as opposed to the left one. So now with the left endpoint, so if we're going to do the left endpoint instead, did not mean to erase those intervals, sorry. So now, instead we're going to take the left endpoint, meaning the smaller number. So now we're going to take 0, 1/4, 1/2, and 3/4. We're going to take the smaller number of the interval, okay? So now our rectangle is going to have a width of a fourth starting here, but its height, the height that we go to, is going to be the output of the function here. Because remember, the height of your function is basically what happens when you stick that number into the function f of x equals x squared. So f of 0, which is going to be the height of our rectangle, is 0 because the function is x squared. So in this case, we actually don't really see a rectangle. We don't see anything there. It has a width of a fourth, but its height is 0. So we're not seeing anything there. Okay. Next up is going to be, now we get something. Now we get this interval, 1/4 to 1/2, this guy here. And then we're going to take the height of the function to be the value, sorry, the height of the rectangle to be the value here. So f at 1/4. Remember last time we did the output at 1/2, so that's why we went up to here. But that's going to be a little different now. So at 1/4, if you stick that into this guy, you get 1/16. Okay, so actually the height of our rectangle now is going to be 1/16. So it's going to be like this. So see, width of a fourth, height of 1/16 all the way through. So we get that. And then we're going to repeat this now when we look at this interval here, 1/2 to 3/4. Now if you stick 1/2 into your function, you get a fourth. So now the height of the rectangle is going to be 1/4, which, sorry, this doesn't align quite well. Okay, so the height of this rectangle is going to be 1/4, and then it's going to go across from 1/2 to 3/4. So we get this. And then last but not least, we look at this last interval here, 3/4 to 1, right there. And again, we're going to take the height to be the output at the smaller value of 3/4. Because see, we could take the height to be anything between here and here. Last time we took it to be the biggest one, this time we're going to take it to be the smallest one. So then now we have a height of 9/16 across here. And then the width is again 1/4. So you can see that as opposed to being an overestimate this time, this is actually quite the underestimate. And then again, the green area, so the area that we have now, so area with left endpoint is just going to be, again, maybe let me call, this one is A1, but it's 0. This area we can call A2, A3, and A4. Again, just kind of listing the areas. It's going to be the same thing. It's going to be A1 plus A2 plus A3 plus A4. And then again, that's just the width of each of these, so the base. So 1/4 times the height. Again, this height here was 0. And then again, the width of 1/4 times the height of 1/16 plus 1/4. Do you see how this 1/4 keeps coming here? So maybe now you see the trick. We can erase this and just do 1/4, and then it's just going to be the sum of the heights. So 0, a 16th, a 4th, and 9/16. Okay. So when we do this and everything clears up, we get 7/32. So this becomes 7/32, which is approximately 0.22. Okay. So then let's just erase all of this and say area with left endpoint is approximately 0.22, sorry, area is approximately 0.22. So then the actual true area, the real area that we're interested in, the real area under this curve, the real area underneath this curve, then I can maybe just erase all of this because it looks kind of confusing. The real area under the curve, which is like in red here, this actual area, which we can call A, we see that A is sandwiched between two things, right? The area A, we saw that green was an underestimate, so the area has to be larger than 0.22, but it has to be smaller than 0.47, because this was an overestimate, this was an underestimate. So we have a approximate area here. So area is approximately this. Okay? Now you may be wondering, how do you get a true area? Like, how do we get the full area underneath the curve here? And basically, you may have already caught on to this, is we only used 4 rectangles, right? Only used 4 rectangles. So what would happen if we used more rectangles? If we use more and more rectangles. So for example, again, let's draw this. I'll just say this is 1. Okay. Let's, for example, say that we chop this up into 8 pieces instead. So instead we say this is an 8, this is 2/8, aka 1/4, then 3/8, then 4/8, aka 1/2, then 5/8, 6/8, aka 3/4, and then 7/8. Okay. What if we kind of did this process again with twice the amount of rectangles? Then what would happen? And let's just say we use the right endpoint, for example. So then the height of my rectangle would be this, and its width would be 1/8. And then this time the height of my rectangle would be this, and again the width is 1/8. And we're just going to keep repeating this process. So the height is that. And then so you can see that this is automatically looking a lot better than what we started with. The amount of overestimation is getting smaller and smaller. It's much less. And so this is the big idea. To get the exact area, we need, how many rectangles do you think you would need to have the perfect amount, the exact area? And because it's calculus, you probably already know it's infinite. To get the exact area, we need an infinite number of rectangles. Okay. Now, dealing with infinity is very difficult in general, but in Calc 1 we came up with this process or this concept that basically allowed us to do an infinite process, and it was the limit. So we're going to use the limit to help us figure this out. So what we're basically going to do is, instead of using 4 rectangles, 8 rectangles, 16 or whatever, we're going to calculate the area with the limit as the number of rectangles goes to infinity. So we're going to calculate the area with an infinite amount of rectangles, and we're going to use the limit to do that. So to begin, let's see, we need to figure out, like, arbitrary, if we have n rectangles, what the area is going to be. So to begin, let's consider this. What is the area with n rectangles? Okay. And now you may be wondering, does it matter if you use left or right endpoints? Well, left or right, if you think about it, and we'll make this more concrete later, it should end up giving you the same amount of endpoint, the same value. Because with the right endpoints we were overestimating, that overestimate will get less and less. But with the left endpoints we were underestimating, that underestimate will get better and better. It will get larger until we finally get to the exact value. So it doesn't matter if you use left or right endpoints. That's completely fine. And then there's like a somewhat of a notation that we use for all of this. So R sub n is, what does that mean? This is the number, the area, sorry. The area with right endpoints and n rectangles. Okay. And then you might suspect what L sub n would be. L sub n is the same thing as the area with instead left endpoints and n rectangles. Okay, so in our calculation we concretely found R sub 4 and L sub 4. So we found those because we were using 4 rectangles. But now we want to figure out, okay, an arbitrary amount of rectangles, n rectangles, what is the area under the curve? Well, at least in our particular case, with the function x squared from 0 to 1. Okay, So let's think about it. If we had, so we were considering this guy, right? 1, 0 to 1. So when we used 4 rectangles, what was the width? The width of each thing was 1/4, right? Because the length of this interval is just 1. So the length is 1. Because, right, you take 1 minus 0. If you think about the interval 0 to 1 on the real axis, this is length 1. And now what we're saying is, if you have n rectangles, you're going to chop this up into n pieces. So you're going to chop this up into, like in our case, with the 4, we chopped it up into 4 pieces. But in general, if we chop it up into n pieces, how big will each of these little pieces be? In that case, the width every time, or the base, so the base is always going to be the length of the base is going to be 1 divided by n. That's going to be how wide each of these are, depending on what we take n to be. So we have now an arbitrary, value n, and this is what the base length is going to be with that arbitrary value. Okay? Then the next thing is we need to figure out what the points are, like the intervals. So last time when we did 4 points, right, if we recall, we had the intervals 0 to 1/4, 1/4 to 1/2, and this right here. So we had these 4 intervals. Okay? And notice that this is going to help us figure out, basically. This will essentially help us figure out what the points that we're going to use were. Because when we use the right endpoints, last time we did 1/4, 1/2, 3/4, and 1, right? Those are the 4 points that we used. But notice that if we take this point here, 1/4, that's our first point, is 1/4, and we add the width of each of these intervals, which is 1/4, we get to 1/2. So we get to this point. And then if we take 1/2 and then we add 1/4 again, we get to 3/4, which is that point. And then if we take 3/4 and add this, we get to 1. Okay? So it's basically saying you take this point here, add this increment to it, it's going to shift this up to the next point. Add the increment again, it'll shift it, shift again. So we're just kind of shifting the point by the width. So then the points that we're using, so the interval that we're going to get in our case now is, when n was 4, this was 0 to 1/4. Instead, it's going to be 0 to 1/n. And then what happens when you take 1/n and you add it to 1/n? Well, you get 2/n. So then this next interval is 1/n to 2/n. And then the next interval is going to be 2/n to 3/n, right? If you take 2/n, add 1/n, you get 3/n. So we're going to continue this process all the way until we get basically n minus 1/n and n/n, which is basically 1. This is just 1. Okay?
So
So this kind of tells us the points that we're picking, the right endpoints. Now we know what they are. They're 1 over n, 2 over n, 3 over n, 4 over n, blah, 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 yada, 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 all the way up till 1. Those are the points that we're interested in. Okay, so then those are the heights. So the heights of the rectangle that we're going to use are going to be, you know, f of 1 over n, which is 1 over n squared, and then f of 2 over n, so this guy, so 4 over n squared, and f of 3 over n, which is 9 over n squared, and so on and so on. So we're just going to keep repeating this over and over again, just for an arbitrary amount, until we get to f of 1. You keep repeating this until f of 1, which we know is just 1, okay? This will go on. So in our case, we stopped at 4, so very small amount, but, and you can see that when we do make n 4, this works out perfectly, because if this is a 4, then this is 4 here, and then what's 2 over 4? Well, 2 over 4 was the point that we had was 1/2, so that works out. And then so this was 1/2, and then what's 3 over 4? 3/4, that's the last point. And then, you know, this was the stopping point. This ended up being n minus 1 will be 3, n is 4, and then this is 4 over 4, which is 1. So this works out very nicely. It's just kind of a little complicated first to see how to write a formula for this in general. And so this is a little tough, but with a little bit of practice and things like that, you can get it down for sure. Okay, so the moral of all of this, the moral of the story here is going to be this, is that now r sub n for an arbitrary amount n is going to be the sum of the base times height, right? The areas that we had. And like last time we saw, we can always just factor out the base, because the base is always the same. So the base was 1 over n, so we factored that out. And then we can start adding the heights, which were 1 over n squared plus 2 over n squared plus 3 over n squared, all the way until we got to 1 squared. We just kept repeating this. Okay, and then let's do a little bit of algebra here. So this is 1 over n, and this is 1 over n squared, plus 4 over n squared, plus 9 over n squared, plus blah, blah, blah. You know, you can think of this as n squared over n squared, right? 1 is the same as n squared over n squared. Seems kind of weird to write it like that, but there's a reason. So what we can do now is we can see there's a 1 over n squared in each term. So we're just going to factor that out. So when we factor that out, we have a 1 over n times the newly factored out 1 over n squared to leave us with just these guys here. 1 plus 4 plus 9, yada, 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 all the way up to just 1, basically. Oh, and maybe, actually, I'm going to leave these numbers. Maybe this is a better way to do this, is to keep this, instead of writing this as 4, we'll write 2 squared, 3 squared, and so on. And so let's redo this. So this will be 1 squared plus 2 squared plus 3 squared up to n squared. Okay, maybe this is a better way of doing this. Okay, so I said that this was 4, this is 9, but it's a little more convenient to just keep it as 3 squared and 2 squared and so on. And we'll see in a second, because now we want kind of the general formula for what this is. And you don't have to know this. This is just some random thing that someone sat there and really thought about what it is. And it turns out that in general, this ends up being n times n plus 1 times 2n plus 1 all over 6. That's pretty crazy. Okay, but this ends up being that. So overall, what we get is that for an arbitrary amount of rectangles, n, using the right endpoints, the area under the curve is going to be given by this. So we have an n times n squared times a 6 in the bottom. So that's going to be 6n cubed. Alright, so n times n squared times 6. So that's 6n cubed times what's just in the numerator up top. Because in the top we have 1 times 1 times all of that. Okay, so this is for an arbitrary amount of rectangles n, using the right endpoint, what we get. Okay, pretty crazy, right? Now, this kind of does simplify a little bit, so maybe let's go here and simplify this slightly just for help, because this n and this n cubed will cancel out. So that's probably the only simplification we get, is that we're just left with n plus 1 times 2n plus 1 over 6n squared. Okay, it's just what it is. And you know, if you plug in 4 here, it's a good practice to see if it gives you the same answer that we got with what we were doing. Okay, so this is where the idea of the limit comes in. We want to figure this out. We want to find the limit. So in words we said we want to have basically an infinite amount of rectangles, right? And n dictated the number of rectangles that we had. So we want to take the limit as n goes to infinity. So let the number of rectangles get really, 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 really big. This. So the number, we want to figure out what this is. And this will actually be the perfect exact area under the curve. Exact. Exact area. Okay? Now, this is stuff that we've done in Calc 1. So if you just multiply the top, just FOIL it out, we have the limit as n approaches infinity of r sub n, which is this, is the same thing as the limit of, we're going to get 2n squared plus n plus 2n plus 1, okay? And then these two just add to 3n, correct? So this is effectively just 3n plus 1 all over 6n squared. And then remember, this is just an infinite limit of a polynomial, remember? And these polynomials have the same degree. If you remember from like the limits at infinity chapter, maybe 3.5, I don't know exactly, but we discussed how to figure this out. And of course, if you have questions, you guys can ask me later, but this is just going to be the ratio of the terms in front of the highest power. So just 2 over 6, because this is a squared, that's a squared, which is 1/3. That's the exact area, is 1/3. Exact area. And let's see how that one fundamental theorem of calculus thing I was telling you about works out here. Because remember, it said that the area was going to be the antiderivative at 1 minus the antiderivative at 0, right? Because we were looking at this function on the interval 0 to 1. So we want to take the antiderivative of this guy at 1 and subtract it from the antiderivative at 0. Well, what is the antiderivative? The antiderivative of that function is just 1/3. Is 1/3 x cubed. So this is going to be, well, if you stick 1 in here, you just get 1/3 minus, and if you stick 0 in here, you get 0. So it's a third. Magic. So this is very amazing, and it saves you this big hassle, but we have to work through this technical detail and this annoying way of doing it first so we gain an appreciation for what's going on and where everything is coming from, because we want to be able to think about it in this level of detail as opposed to just resorting to this fancy theorem, you know, because then we don't really know what's going on. And then if you do this with the left endpoint, the same thing is going to happen. It's kind of the moral of the story here. So whether we use the right endpoint or the left endpoint, if you get an infinite amount of rectangles, you should get the same answer. Okay, so now this was a nice example to kind of justify or motivate, I guess the better word, for the definitions that we're going to have. So in general, say we want to find the area of the curve. So in general, say we want to find the area curve. So we take some arbitrary function and we consider it on the interval a to b. So a and b are completely arbitrary. Now, in our example, a here was 0 and b was 1, and this was x squared. But we want to kind of do this in a general setting so that we don't have to keep kind of like thinking about what's going on as much, so we can kind of streamline this process. And we will get to this on the next video.